It's wonderful to be visiting virtually. I wish I could be there with you in person, but lots of good memories working with Ross and the games group with Vadim, rest of them, AI and computer science department. And yeah, lots of good memories of Edmonton. Okay, so I'll be talking about the most recent work within what I call prediction games. This is online probabilistic learning, and it came up. The problem came up. I was trying to write a system for prediction games, and gradually it matured. I thought I would spend 3 months writing it, and I'd be done by the fall of 2023, and it took me a year. So yeah, it's been I think progressing really well. Good ideas on different topics. I'll try to touch on a lot of subtopics here, and I hope to give you a taste. But yeah, I'll go fast sometimes, and I'm hoping that uh, you get an understanding of the different challenges. And it's new, so yeah, if you think about related work, et cetera, definitely maybe after the talk we can discuss. So yeah, let's get on. And again, this is the most recent work. But before that, like a stack of things I've been doing, this is the next to last. I was working as Ross mentioned at Cisco, 10 years, and we were developing systems that sensed the traffic within your data center of, let's say, hundreds, thousands of your machines. You are an enterprise, like a company, like a Boeing, or even like LA County, different governmental or private businesses. They have the enterprises that have an internal network of machines, right? And you want to secure them. The traditional approach has been to define a firewall that sits at the perimeter, and it's not secure enough. So we would basically define a policy, help define a policy, and experiment with that network policy and enforce it at a very much more fine-grained level of hosts or groups of hosts. And there's a lot of sensing that has to be done to figure out what are the appropriate network communications, what edges allow and what edges to drop. And yeah, so each host to host, there's a channel. We would define a space of legal traffic to allow and drop every other thing, right? So you got to be, when you are enforcing it, taking the actions, you got to be careful. Your customers could be medical providers, right? You don't want to drop packets there. So lots of machine learning there, grouping, clustering, defining these policies, and then enforcing. But and so that this basically, once you have these more fine-grained policies, it's much harder to attack the network. If a bad guy infects one of your hosts, it's much harder for them to laterally move and infect your most precious databases and so on. So this is a way of slowing down attacks. But this segues to my talk: is how do we build systems that are learning and so on, and that can stand on their own? We would ship this product, right? And we don't have any, we can't handhold it anymore. We can retrain things and so on very aperiodically, and the customers don't want to share their data, right? So this system, there is a UI. Fortunately, there is a human in the loop, but they have to stand alone. So how do we go towards systems that are more and more independent? And I think learning and development is a big part of that. And I really like this quote by Merleau-Ponty, who was a philosopher of especially phenomenology. So this quote really resonates with what I'm going to present. Occasionally a new knot of significations is formed, and our natural powers suddenly merge with a richer signification. Yeah, so over time, every so often, our learning systems develop skills or patterns, and then they incorporate it. And what I'm going to talk about is potential, a story of part of how this could be happening, as a possible story for how this learning and development could be happening. So I'll talk a lot about the setting and motivation, prediction games, and so on. So that could be maybe 2/3 of the talk, about half hour. And then I'm going to zoom through a range of topics, evaluations, the methods. Just going to touch on them. I'm not going to go into detail. Hopefully, I have your interest. I'll keep your interest and so on. It won't bore you, but yeah, won't go into a lot of details either on the experiments. So, but hopefully, yeah, you get a good taste of what this is about. So 2/3 of the talk there, and then the last 10, 15 minutes is about, evaluation means you have different prediction techniques. Which one is better on your sequence, right? How do we rank these things? And that's actually challenging too. And then the methods, the moving average techniques online, and also then the data and the experiments. So stationarity, when you live long, I'm in my 50s, you do see a lot of change, right? So we are all accustomed to change. It's basically natural. There's all changes occurring all around us, external change especially, right? Daylight to nightlight, seasons change, weather changes, political events, and so on, right? Language use. Some of them are fast, some of them are slower, seconds to days to months to years, decades, right? So that's external change. By the way, I like really the work of Tim Ingold, who's an anthropologist, writes about anthropology and the philosophy of it, phenomenology, especially this book, The Perception of the Environment. He has a chapter on the temporality of living and so on, essays on livelihood, dwelling, and skill. So with respect to you, the observer, recognizer, these are external non-stationarities, right? And as builders of learning systems, we don't have control over external non-stationarity. We just hope that it's not too rapid or drastic that would make machine learning infeasible, right? So that's external change and non-stationarity. And I play volleyball, and if you plot the typical person's jumping height, you can see that it grows maybe in the late teens and 20s. It max at its max, and in the 50s, you can only jump a few centimeters. And the landing is a problem too. So is this an external or internal change? I don't know. You can think about it. But let's talk about what I call internal or developmental non-stationarity in particular. So as we write learning systems, right, they have different parts in there, and these parts interact with each other and need to adapt to the changes among themselves. And that's the internal choice. And some of them may be even growing. And so this sort of internal change, as designers and builders of these systems, we might have some control over that. Okay, we might even be able to model it to some extent. So that's internal change. And I think it's a good distinction to have. And let's make it a little more concrete in terms of prediction games. So what is prediction game? That I came up with these ideas in mid-2000s. It's an unsupervised, now it's called semi-supervised machine learning approach for learning. Again, the issue of a system that you want to stand on its own, to develop and learn on its own. So in the particular game that I write, it's in text, natural language. So the system starts at the unigram character level. Those are given to it, and it should play the game, and over time, starting from characters, go to words, phrases, and so on. So builds its own growing hierarchical network of concepts. Begin with a small alphabet. Those are the givens, the hardwired, the primitives. So the latest system is, I call it Expedition, and again, mid-2000s came up with these ideas. How do we, extend machine learning? And, humans and advanced animals seem to learn a lot from the time they are born. And it's not all supervised learning. Definitely reinforcement learning is a big part of it, right? if it's not supervised, but supervised learning techniques are so successful, how can we adapt supervised learning to give us insights into how, and build systems that are more independent? There's active learning. Russ mentioned that. There's user unlabeled data. I mentioned our reinforcement learning. How do we put these together? So-called close the loop. The system, the things, the artifacts it builds, it should reuse them. Okay. How do we close the loop? We have lots of clustering techniques. Can we use those online learning techniques and so on? But the system has to use its own artifacts. And so I always remember House of Cards, because there's a lot of uncertainty. And how do you make sure the algorithms, the things that you make, the uncertainty and the errors that you make don't compound, and your system doesn't get into a rut, a local optimum. There's a lot of problems. And so I propose this as a research direction. Okay. And so I put a pause to this for 10 years and came back to it, I think, around COVID time. So you have COVID to thank. So yeah, so like 3-4 years ago. And I've been very happy in terms of the ideas that come and the progress. So one distinguishing factor in this approach is that concepts, these percepts, n-grams, let's think about it in text, n-grams, are both predictors and predictands, targets of prediction. Predictand is that which is to be predicted, the mathematical sense. So concepts are both, if you like, have outgoing edges, develop these outgoing edges, and incoming edges as being predictand. And again, the word predictand are used to say targets of prediction, but fortunately, recently I found that English has the language has the concept of predictand as a word, so that's good with a D. Okay, so expedition. Another concept is segmentation. I used to call it segmentation, but now interpretation. So it interprets each input episode. And an episode for us is going to be a line of text, a fragment of text, right? Interprets each input episode with its current concepts, that it's growing, this set of terms. And so interpretation is the process of mapping the observables, the primitives, the unigrams, into the highest level concepts that the system currently has in its repertoire. Okay, it has to do this efficiently and in a robust manner. There's a lot of details. This is still, I researched it and so on, but that's the idea of interpretation. And it uses prediction to do this. Prediction is a big part of interpretation. So it's a process of mapping observations, the primitives, to internal highest level concepts. Okay, it requires some inference, some search, but the hope is that by playing this game, by practicing interpretation many thousands and millions of times, the system becomes smarter and so on, comes up with more capable concepts, so forth. And again, it's for perception mostly, like for vision, but I'm playing this game in text because it's simpler, right? Text is one-dimensional. Obviously, you can have pros and cons, right? Text has a lot of hidden regularities too. I don't have to sell you, I think, prediction that it's a unifying task, right? You see language models nowadays that do everything. So higher level concepts by predictive power. For example, in English, zoo, the word zoo is more informative than Z or Z, right? Of the unigram. So they buy the system more predictive power. And I wrote a paper last year about, how do you formulate this in terms of an objective or a guide? It's an information theoretic objective that I call core, that quantifies this predictive power. So something like core could guide the system. Okay, but these new concepts cause non-stationarity. And that's the non-stationarity, the concrete case of internal non-stationarity. Then use of newly generated n-grams during interpreting changes the distribution for existing concepts, for existing predictors. So concept generation causes new concepts, gives you more power, and concept use, it's like a producer-consumer, right? But really both of them are producers. concept use interpretation, and the interpretation, because there are newly generated concepts, it's there is non-stationarities. Um, I'm going to have a concrete example in the next slides, but the important factor is that for concept generation, you have control. You're the system designer has control in terms of how fast or slow they're gonna, like a faucet or a spigot, you can turn it off. In some of the experiments in this paper, I completely turn it off. I just play the game at the character level, right? So that's the idea of internal non-stationarity. Let's go to the endless meetings. I said this was the text in one episode, a line of text, and E as a character is a predictor. So E tries to learn what comes after it in terms of other concepts, in this case, characters, right? And after some learning, E develops these edges. And these are the predictants, other concepts. Now consider N, and N also. Every character is both a predictor and a predictand, okay? And these edges have probabilistic weights, the conditional weight. After E occurs, what's the chance of A occurring right after? It's 0.1, 10%, for example. Okay, but after some learning, let's say now the system has learned to interpret, its highest level is, let's say it has generated the concept ND. So after E, sometimes ND occurs. E doesn't see N anymore. It sees ND as a whole. Okay? And so after some learning, we wanted to downweigh N and upweigh learn ND. ND used to have 0 probability. We wanted to now predict ND some of the time. So N has to go down. Okay, the probability of N for E. So this is the other concepts, the other predictands, hopefully should not change their probability that much. We should not interfere with them if they're not changing, right? It is kind of a local change. Similarly, for N is not going to be active as much anymore at the highest level, and D has taken its place. So the distribution around N has changed. And also ND is a new concept. We need to develop edges for ND. So we want prediction techniques that do this in a timely manner, can adapt to this internal non-stationarity. So that's the motivation. And the file, the text corpus does not change necessarily. Assume it's a big text corpus. Each time you pick a random line, it's a totally a stationary world outside. But internally, this system is changing. Next time it sees the same input line, it should interpret it in a different way. Russ or somebody have a question?
Just to confirm, the set of probabilities after it adds up to 1, right? So
yes,
it's disjoint options, even though N and ND, they are related. This is implicit N without a D followed.
Yes, yeah. The E is seeing ND, and that's why they are mutually exclusive, even though N is a prefix of ND. A good question.
Thank you. Thank you.
So recent developments, it's become, the prediction games have become much more probabilistic, information theoretic. I mentioned core, utility driven. These concepts that you build, they are somewhat heavy. So the system has to spend some time developing them, right? In be choosy, what concept to generate, how to, So the quality of these edge probabilities matter. So the old way, that is 3 years ago, I would add layers once in a while, occasionally. And then because of this non-stationary, I would relearn everything, right? But this is discontinuous. And what if your external world exhibits similar non-stationary patterns? So with the new techniques, the new moving average techniques, it's much more continuous change, much more, it's very nicer, right? Smoother, faster transitions, more adaptive to this sort of change. Okay, so now we're going to go to the problem setting with this. By the way, here we don't use back propagation. These concept generation all should be heavily researched, and I'm not going to focus on interpretation or concept generation. Now just the prediction task. But you can see the setting. You can see at least one place where these things might arise. Okay, so the problem setting is time is discrete. 1, 2, 3, right? And items are observables are discrete. At each time point, you see one observation. So from left to right, you see B first, the letter B, A, and I show observable O to the power to the superscript 2, right? This is not to power 2. So that's O at time 2, observation at time 2. It's a multi-class. There's only one observation. We just alluded to that. Okay, so that's the notation. The set of items is not known to the predictor, and it's a growing set, and you can think of it as infinite. Okay, so it's infinite, like integer ID, 0 to infinite, right? But it's not known, and sometimes in the examples I use letters, right? A, B, C, D. The predictor has finite space. It's not growing. It's the space of computation it uses to predict next. It doesn't grow with stream length. So just constant space. So what does the predictor do? The predictor outputs distributions or semi-distributions. The probabilities may not add up to 1. It may converge to 1, but we allow it, right? Initially, it has nothing, and gradually it outputs more and more. So initially, it was outputting empty set, and then A with probably 0.5, then it changed it to 0.7, then it started outputting B, and so on. So it's a semi-distribution. And we denote these semi-distribution candidate distributions by W's, W1, W2, W3, W4. So example non-NTSD is with these two items, A and B. So support of W is A and B in this example. And the sum is the 0.6. To compute, to evaluate, we use the log loss or cross entropy logistic loss, okay? So it's just the probability assigned to the observation by that model at the time. So yeah, and then we average it over the sequence length, our test sequence length. So why probabilities? Why semi-distributions? Why are you taking log? There are other measures. We'll get to that. But probabilities, I kind of motivated it that we are doing utility expectations, for interpretation. We care about good probabilities. Why semi-distributions? Well, the predictor shouldn't come up with a full distribution right away, right? And why shouldn't it add up to more than 1? Why individually? Well, because we're doing expectation. We don't want the predictor to cheat. So these are quick answers, but yeah. Non-stationarity means that, yeah, the stream might change over time. So initially you see a lot of A's and B's. At some point you might see W's and B's. A's is gone. The idea, this is the idealized non-stationarity that I'm designing these algorithms for. So you have an underlying probability distribution, categorical distribution, discrete, and you sample IID from it. But once in a while, we don't know when, some of those changes. In this example, some of the items probably, A gets dropped from 0.7 goes to 0. B doesn't change, it's 0.1, 0.1. C comes in, H comes in, and W goes up from 0.05 to 0.5. So as I was designing algorithms, I realized that this is the target ideal that I have in mind, right? I'm reluctant usually to assume much, as a designer, right? But this is it. That's what I have in mind, actually. And of course, the real world, it doesn't follow these things, right? There's no IID in the real world. There's a confluence of processes that conspire and aggregate to generate a sequence for you. So it's important to test on the real world. But this is, and it's similar to Bayesian, but I don't think it is a complete Bayesian. I'm not assuming anything about the generation of P1 and P2. By the way, these P1s and P2s are semi-distributions. They sum to less than 1. So what do you do? What does sampling mean from a semi-distribution? So one way to define it is whatever it's not allocated, the remainder from 1, you take from a noise distribution. Some item that's not going to appear at all, only once in a stream. Okay, that's noise, and that's one possible way. So that's the noise model that we can keep in mind. So the P's, the underlying SDs, are not seen by the predictor, and we would like it to converge to these as soon as possible. And because the predictor is finite space, one way to say it is we are interested in probabilities above a certain minimum, like 0.01 or 0.001. So estimate probabilities above this threshold. And if you want to lower that threshold, you need a bigger a space predictor, and the world should be that way too. Your external stream should have certain stationarity, that things that happen 1 in 1,000 times have some meaning, right? But yeah, that's the truth. And so that's a conjecture that we don't, we need only finite space predictions, and probabilities beyond a certain point. We are interested in that. We're not going to lose much by trying to model lower probabilities. So if you zoom out, these are the underlying probabilities. Once in a while they change. Within a change, there is a subsequence that's stationary, right? It's a stable period. The world is a stable, static, the world is dynamic. These two statements are not necessarily in a contradiction, right? As long as you have an understanding, you're going to modify the world is stable mostly. For most items, it's stable, but it is dynamic. Sometimes, for some items, things change. So it's always some thread of change, right? But it doesn't have to be the same item all the time, and it doesn't have to be all the items. So for more, the both statements can be true at the same time. So as we zoom out, our techniques will be going up and down. Some of them have a learning rate that go up as soon as they notice a change in the distribution. And this reminds me of Cisco's logo, which is the Golden Gate Bridge, which is a bridge. Cisco is a networking company, right? Yeah, Cisco, the name comes from San Francisco, if you didn't know. So San Francisco Bridge, and the current logo as of 2024 is this thing. And we want efficient algorithms. So there is a streaming algorithms, for example, in the data mining, but they usually assume we can do one or multiple passes. They're thinking of one prediction or one or few. But we want to write algorithms for thousands, hundreds of thousands of predictors. Each of our concepts, right? Single characters, bigrams that are generated, and so on. They are their own predictors, and they get their own stream. So it's like a single instruction, multiple data streams, parallelism. They're not always going to be active at any episode. Only few predictors will be active, but we want efficient algorithms for such. It's independent. So a little, just this is just about semi-distribution is a distribution where the sum is at most 1, the sum of the item probabilities. The probability I use PR in the paper is a real value between 0 and 1. A distribution is a special case of semi-distribution. So in 3D and 2D, I'm showing them, right? SDs live inside the simplex, not necessarily just on the surface. And you can imagine it in even 2 dimensions, even 1 dimension, you can have DI is a point and SD is the interval. And 4 dimension is exercise, right? For how to visualize them, 4 and 5 dimensions. Questions? Sounds good, sounds good. All right, evaluation. You might have seen this code. All models are long, some are useful. By George Box, who was a son-in-law of Fisher. All right, so evaluation. In synthetic experiments, we have the actual underlying probabilities, and we look at the ratio. At any given time, we say, okay, is any of the items in the distribution, take the ratio W of I to P of I, is it greater than D, some deviation threshold? Let's say 2 or 1.5 or 1.1 or something. Take the max of the ratio of W of I to the P of I, and okay, how much is the deviation rate? Obviously, first time you see an item, the predictor doesn't know, right? It's going to give it 0. So will be deviation. Why not the difference instead of ratio? Again, we're talking about taking utility, and I think ratio is what matters rather than the difference. Like quadratic loss, there are losses that are much more well-behaving than log loss, and but they are not good in this sense. Okay, so but in the real world, we don't have true probabilities. What do we do, right? And there's we take each letter and see what probability your model gave to that letter, right? Each observation, and just average the log of them. Okay, and that's it. The problem is log explodes in your face, right? When the W is 0, when the assigned probability is 0. So what do we do with that? Again, there is other ways, quadratic laws, but let's say you were interested in one in uh, 20 event, 0.05, right? It happens once in 20 cases on average. And your model gives it zero. Well, that's a big sin, right? You don't want it to give it zero, give that item zero probability. Um, but quadratic law says, hey, that's the difference of 0.05. And if another item had probability half of the time, 0.5, and your model gave it 0.3 or 0.4, the quadratic laws will be most sensitive to that. So there's a space in the paper talking about why not those well-behaving laws, quadratic laws, why log laws. And then, but you have to go through the headache of explosion, right? So what I do is use a referee, a simple algorithm that says, okay, is this item uh, out of vocabulary? Is it a noise NS, non-salient or not? Simple item. And I say, okay, methods that do well, subject to several thresholds for this marker, um, are good. So that's how I do it. And also I cap the logs. If the if the prob if the observation there's a policy. If you had if the probability was there, you give it a negative log. Otherwise, this is the policy that so it's a little has a few more steps. Uh,
The
and
piece of NS is a constant you give the system.
excuse me.
The piece of NS is a constant that's part of the input to the
Yes,
process.
for evaluation. Let's say we were only interested in probabilities above 0.01, 1 in 100. P sub ns is 0.01. In most of the paper, it's 0.01, yes. Yeah, so you can see that, okay, so the is ns is your simple referee. And we play with different thresholds for referee. So it keeps it's like a box predictor of the last 100 or few hundred and has a threshold. If I have seen that item in the last 100 time points twice or three times, then it's not noise. It's not ns. Otherwise, it's ns. And if in that case, we cap the loss, right? If both your predictor and this referee agree, you will give it the allocation of for not noise and otherwise this. And here's the uh, example. So if you always generated noise and then there was only one item and it grew in probability, here's the one salient item. If you always generated noise, actually you get zero loss. The lower, the better. And if the item, that one salient item goes up to probably 1.0, again, the lowest loss is achieved. And in the middle, the high entropy case for one salient, you get this. In the middle is the highest loss. And as you add the number of items, this is the maximum possible loss you get. So the idea has been that we want to evaluate these different techniques, and we don't want the non-salient items to dominate the comparison, right? Log loss can be very sensitive to them. This is a way of doing it. And now, is it proper? Propriety means that are your techniques truth-telling? And there's a lot of literature on that in forecasting and so on. There were some citations a couple of slides ago. And it's very, impressive and magical that it kind of works. And we show that it is almost proper. Doing these things causes some distortion, but not much. If your probabilities are high enough in your true generating probability distribution, we limit the distortion. That limits the distortion. So we characterize when you get distortion and how much. Yeah, so that's the near propriety, and we're going to use this log loss. Let's go over the moving average techniques. The three techniques are again, zoom through these things very fast tour. EMMA, the Q's technique, and a combination. Okay. Questions? So all methods keep maps. Let's start from EMMA, which basically a predictor has several predictands, right? Tens to hundreds. Again, that probably PNS or PMIN puts the upper bound on the number of non-zero edges. So every predictor has some number of edges, initially maybe zero, and each of these edges have a W, which is the probability. These probabilities are learned over time, okay? In the Qs, Each edge is associated with a queue. It's a buffer of counts. And from those counts, you derive probabilities. And in the dial, for dialing up learning and lowering, it's a combo of these two techniques. Okay, more overhead, sorry. With each edge is not just the queue, but also a probability and a learning rate. Not a few more bytes, right? Or a probability is what, 2 bytes maybe? A queue with a small queue, capacity 3 integers. And this is the sum of those. Beta is the learning rate. So you keep a learning rate for each edge instead of one fixed rate for each node. We used to have it that way for each predictor. So updating and prediction will be order W, size of the number of entries in the map, okay? In your semi-distribution. Yes. It could be even faster. For queues, it could be order 1. So here's Emma's update in a qualitative fashion. You weaken all edges upon an observation. Let's say A is observed. You you boost the connection to A. If it was 0, you insert the edge. Otherwise, you strengthen it. That's the qualitative conceptual. And you might remove some edges. You drop some edges if they become too small to keep the memory consumption, right? And here's the more quantitative. Beta is a learning rate between 0 and 1. The weakening step that I mentioned is you multiply everybody by 1 minus W, or your connections, and then you boost to the target, to the observed, by beta. And if you do this, you can show that, it's there are many properties. Gradually, we develop these properties as we needed them. So for example, it's always SD. If you start with a semi-distribution, after the update, it's going to be a semi-distribution. The sum of the values of the semi-distribution converges to 1. 1 is a fixed point. You can show all these things very nicely. Okay. Many nice properties for MR. It's a convolution in time. It's a filter. And I put some of our early work with this. And it has roots to many class index learning, efficient online, that many people we have collaborated with, including someone's brother. And MR is a moving average. If you roll it out, you can see the learning rate goes exponentially to the past. So the history, the old history, what you observed 3 times ago or something, it's exponentially down way. That's why it's called exponentiated moving average. You can look at it as inflow and outflow probabilities as you weaken and strengthen. You have an implicit reservoir of probability mass. It's initially 1.0. It goes in and out as you update, weaken, and strengthen. Emma's convergence, a few quick slides on this. We're going to talk about one of these weights, W, in the stable regime. Okay, there is one probability distribution that's generating data. It's not changing. We show that Emma converges. And different learning rates give you different convergences. Okay. And again, the issue of juggling multiple things. Do you want a high from learning rate or low? Both have trade-off, right? With a low learning rate, you can refine your estimation. The statement is that it converges to within beta of your target. The estimate that you have over time, it's a discrete random walks. You converge to within beta. Yeah, so the convergence is about in terms of expectation. Every move has 2 possibilities, but the expectation is always getting close to the target. Maximum motion is beta, and minimum motion in expectation is at least beta squared, as long as you're outside this band. And it, in many senses, it's like the physics motion of a pendulum or a periodic motion of a spring. The farthest you are from equilibrium, the more acceleration you have towards the stable. But this is a probabilistic version of it. And so there is a gap here in the theorem of 1 over beta squared. But in general, you're dependent on beta. And you want a small beta because you want to handle probabilities that are fairly small. But the higher probabilities get a hit. You're not going to converge to them very fast. So theoretically, it would be nice to reduce this gap. I haven't looked at it. But yeah, there's this trade-off, plasticity and stability, right? Between keeping a low rate or a high rate. There is a partial solution, harmonic rate decay. If you start the rate high and lower it using harmonic rate, you can show it's like plain averaging. And what that says is that for high probabilities, you can converge very fast. But you can do this only once, yeah, right? With a learning rate, start high enough. What if new items come? And it's not flexible enough, and you can show in this is a plot of the convergence. It's harmonic rate decay is it's more flexible, but you need change detection. Q's is a way of high variance technique, moving average, that does better change detection. You keep a Q for each item, you update on a positive, and on an it's kind of like the other one. You do a negative update for everybody for all your Q's as a predictor, and then add a new cell when an item comes in with a value of 1 for that item, for that Q of that item. And you drop Q's that are too old, predicts has high variance. And this is a quick simulation of that. Sorry, I gotta go fast. But every time you see an item, you create a Q for it, a Q cell for it, and you keep the capacity of Q within some small capacity limit, 4 or 5, for example, in most of our experiments. But there are a variety of ways of extracting probability from a Q. There's a best way called minimum variance unbiased estimate. This one as a conjecture, I put it on a stack exchange that, okay, I have upper bound and lower bound. I think these are upper bounds and lower bounds. And somebody right away on a statistical stack exchange, John Bauman, gave me the actual and that the minimum variance, there is an unbiased estimate like that. But you need to use the cell 0, which is much more dynamic for each Q. It's incomplete. I can't go into details. Sorry, we can go maybe after the talk. But yeah, so for non-stationarity, you need to use cell 0 of the Q. Again, thank you, John Bauman, and Rao blackvalization. The technique for deriving the unbiased estimation is called Rao blackvalization. And this is a paper that uses this for. So in a Q, basically, you keep track of each item as you see it, and you discard the item some of the time. This is the status of an item. It might stay, and you might be always forever predicting probability, or you might discard it all the time. But you always keep track of every item you see in your stream. You may not predict right away for a probability for it, but you're keeping track of it. But so there's a lot of properties that Qs have. As we said, there's variants that make it even more efficient, timestamp variance and the box predictor. And let's go to dial, which is the combination of these two. Qs is high variance. Dialing up the learning rate and lowering the learning rate has a learning rate per edge, per predictand. And it does the regular EMMA, but some of the time it listens to the Q. It keeps a Q too. So when does it listen to the Q? There's a binomial test, efficient test, order 1 per edge that does that. I'm not going to go into details, but this binomial test is a good thing to know too. It comes in handy. There could be other ways of doing it. This is, so there is some overhead, but asymptotically, this is similar cost. A few more bytes per edge. So experiments, this is an oscillation experiment. The true probability, it's a binary experiment, a stationary, a non-stationary 0.25 and 0.025. And you can see that you check the probability to 0.25 and bring it down to 0.5. So like that, right? And you see that EMMA's estimate with a fixed rating rate, plain EMMA, it's slow, but dial quickly usually converges to the 0.25 or 0.025. If you have Qs, you can see that it has relatively higher variance compared to those two, Qs of 5 and 10. This is a close-up, or at least showing the learning rate of a dial, and the red dot is when it notices the change. It's not perfect. Sometimes it misses the change. But when it does, the learning rate shoots up, and so it looks like the Golden Gate or a spiking network, right? And here's a close-up that I was talking about. from 0.025 to 0.25, 1/4 of time, you can see that the learning rate shoots up. Okay? If it detects it. This red dot means it detected it. Initially, you see Emma's estimate goes up if it didn't dial, but then it really gets close to the actual target probability. And you can show tables in synthetic experiment. The lower the log loss, the better. And you can see that dial usually does better in several situations, several settings compared to the other techniques. Whether you use the rates, because here in synthetic experiments, you know what the deviation rates are, or you use log loss. So yeah, there is a reason. If you had stationary streams, then just use regular Emma with an appropriate rate. But if you have changing streams, dial can be better. So real world, I'm not going to, so there's work on expedition. I got sequences from expedition, but also Unix commands from Greenberg, from University of Calgary and others. And this is a typical learning curve. Your learning rate, again, the lower the better. Dial is much less sensitive to the choice of your learning rate parameter versus fixed rate Emma or harmonic rate decay Emma. The top ones are harmonic rate decays. So again, you can do sign tests and so on and show that, dial is usually better. So here's the learning rate of one concept within expedition called 10. The concept is 10, T-E-N. At some point it gets created, and after that you can track its learning rate over 200 episodes in this case. And you can see the median learning rate. Remember, dial has a learning rate per edge of the predictor 10. Goes down, that's the median. Okay, but the maximum learning rate, some of the time goes up, right? When a new concept it has to learn. And number of predictants is the total out degree of 10. You can see it goes to 20. And here's another one for the concept I or L. Using that, you can see I'm only showing the maximum rate over 12,000 episodes. It shoots up some of the time. And this is the out degree. And this is other like Unix data and so on. And if you concatenate, you can see the learning rate as it goes up. These are plots of learning rate. So summary, the dynamic words require dynamic learners. They require a lot of things, but one part of it is dynamic learning. We talked about internal versus external non-stationarity, how we can have a knob for internal or developmental non-stationarity. We talked about multiclass probabilistic prediction under this non-stationarity, developed several sparse multiclass techniques. The Q technique is very responsive to change, but has high variance. You have to increase its capacity a lot to gradually lower the variance. So it takes its space could take a lot of space. Emma can have low variance, but has high bias in effect, and so can be slow to converge. The combination has some overhead, but can enjoy the benefits of both, and that requires per edge, per predictant learning rates. Number of future directions, obviously improve these algorithms, but try them within expedition or prediction games and see how they work, right? Maybe Q's is good enough, right? It has high variance, but it's simpler in many ways. So, and also, there are other questions regarding the items can have rewards. So can we incorporate rewards in online learning? Thank you so much for your time. And my team at Cisco and my research team at or reading group team, Tom Deans. Thank you, John Baumann. And yes, this is the complete code of Maurice Merleau-Ponty. Thank you again. Any questions?
Any questions? Could you show the update rules again?
Update rules for Emma.
Sure.
And then we can go to Q's because I jumped over Q's very quickly. But Emma, let's go with Emma first. Was there a question? I'm sorry.
Is this, and what would the gradient descent? What is W?
Good question. Is this a gradient descent? In one of the papers, we show that this is actually a gradient descent in the EMMA's update. Is a gradient descent if the objective is quadratic loss in the probability estimation. If it's quadratic loss and you take the derivative, the EMMA update comes up. Quadratic loss for a probability estimation of the target.
What was W? What is W?
W is your edge weight, your current and new edge weight. So W is capital W of I for a given item. Lowercase w is one of those smaller edges for item I. So before update, it's W. After update, it's weakened. It's lowered by 1 minus beta. If you multiply 1 minus beta by it, it's going to go down.
And how do you get probabilities from them?
Okay, so if W is already a probability, let's say it's 0, then weakening it gives you again 0. But then if you boost it, you're going to get beta higher. So it's going to be somewhere between 0 and 1. These things converge to the true probability of the item. Interesting.
It always adds up to 1.
And
it always
adds up to 1 or less.
Okay.
1 or less. It's a semi-distribution, but you can show that, yeah, these individual W's converge to the conditional probabilities. And the theorem quantifies it, how for fixed rate EMMA, fixed rate. Yeah, it's initially it's 0, but goes up and converges to the probability.
No projection needed.
And no what?
No projection to the
no calibration.
Like complete simplex, semi-distribution simplex. You don't need to project into it.
No, I don't need to. It converges to it. If it's a stationary distribution that's generating the data, it converges to it. Yeah.
Thanks. Because with the stationary distribution, it's a very easy problem, right?
Yes. So the whole issue is how fast does it converge? Because I'm saying that the distribution is changing over time. That a stationary distribution once in a while changes, right? And so the whole thing is now, okay, it converges, but is it fast enough? And even though EMMA is fairly adaptable for non-stationarity, is not fast enough, at least for our application. Hundreds of the steps to converge is not fast enough for a given edge. We want it like in tens of the steps.
Thanks.
Yes, and this is per predictor. I had focused a lot on aggregating multiple predictors, but now I said, okay, let's focus on one predictor at a time. Usually in machine learning, we talk about multiple predictors. This is like the naive Bayes, multi-class naive Bayes, but in a non-stationary setting. What would you do to adapt naive Bayes for a non-stationary setting? But another question is, how do you aggregate these things? Again, a lot of online learning has looked at that for changing environments. Yeah.
I have a question from left field. Lempel-Zip, the compression algorithm, which also tried to find like sets of things that appear many times. Is this related to it? Is this be different from it? Do you know Lempel-Zip?
I mean, I know a little about compression techniques, and compression is definitely related to machine learning. Lempel-Zip. I mean, what they do is compression is usually doesn't care about generalization. It's about this file. I'm going to compress it the best you can. Don't care about.
Try to find patterns that appear multiple times, like your example about N and ND and things. Try to find a subset of a sequence of letters that appears more than once and gives us more number of bits for that. To me, again, from left field, I'm just thinking about the earlier motivation.
Yeah, exactly. So definitely here, the system is sensitive to frequency because it's sensitive to utility. So if ND appears multiple times, it says, okay, I'm going to make a concept about it. Yes. And so any technique, I mean, I'm researching still techniques that can do a good job. In natural language processing, there are some techniques, etc., that can generate good concepts, good n-grams. and more general even that finite state machines. Can we do that in an online, robust manner? But yeah, so frequency is definitely a big part of it, a big component. Another is, predict. How well does it predict and gets predicted?
Okay, it's not the same problem, but the idea of saying, I found this sequence of characters that appear multiple times, and now I'm going to compress that to a small number of bits. Okay, so it's just again from left field, but sort of as you were describing, I thought about that.
Yes, definitely. To a good as much as at least compression relates to the learning, machine learning. But yeah, a big part that I want to go back to now after doing this is the concept generation. How far can we extend this expressiveness of concepts? I'm assuming that if I get to a level of certain classes of finite state machines, that's powerful enough. And there are some works in vision research conferences that I've seen that do some that, especially before neural networks became very dominant. But yeah, so concept learning is a big part of this. And how does it interact with the other parts of the system? But yeah, the expressiveness of the concepts that you learn. Simple concatenation has been successful, as you said, based on frequency. And they have to fight these concepts because they shouldn't overlap with each other that much within an interpretation. But yeah, frequency is a big part of it, but not the full story.
Great. Thanks so much.
Thank you, Omid.
Thank you so much for your time. Yes.